Welcome to the optical communication course. Today we will learn that a model 3. In that model 3, we will learn a sources and a detector. So now that what are the various optical sources and what are the various optical detectors used in a optical fiber communication that we are learning. That sources are two types. One is about a laser and another is about a LED. Now if you see that both the devices, they are made up of a semiconductor material with additional impurities to give up the photon of energy. Means recombination of electrons and holes takes place at the junction, so that will produces a light or it will emit the photon of energy, and that photon is nothing but a light. Now that is about is LEDs and laser sources that we are learning here today. Then according to that we have a detectors, and the detectors, that is a photodetector. That photodetectors detect the light and convert into a electrical signal. So we will learn here a pin diode and a photodetector, that is a avalanche photodetector. Okay, or avalanche photodiode. So now in this case, if you see that for a optical fiber communication, we need a light source there, so that light will emit through the optical fiber. This is about our sources can be LED or a laser here, and then here we have a detector. This light falls on this detector. Okay, when light falls on the detector, then it will convert that electrical signal. Now for the given particular source, if you see that here we are providing a current pulses, and that current pulses are propagating, means current pulses are converted in the form of a light, and according to the source we have used, that LED or a laser, according to that conversion of that current converted into a light photon of emit, and then inside the fiber your rays are propagating. These are nothing but the light rays are propagating through the fiber, and that is propagating through the core of a fiber here, and this one is nothing but a cladding here, and then we have a detector at the end. So whichever the light emits from this fiber, that will be accepted or that will be detected by the detector, and then it will generate a current pulse there using that light there. Conversion of whatever the rays in the form of a light rays, that will be takes place at the detector itself. Means whichever the informations we have, that is in the form of a voltage, that will be converted into form of a current pulses, and that information is propagating through the fiber using the source there. Modulation and everything takes place at this particular place, and here similarly we say that the modulation takes place at this particular place, so that we'll get that particular current pulse here. Now till today we have learned that what are the various optical fiber. That various optical fiber, that will be a single mode or a multi-mode fiber, and then we have learned that a step index fiber and a graded index fiber. That is about it, two types of fiber. Now then, which source is suitable for this single mode or a multi-mode propagation, or which source is suitable for this step index fiber or gradient index fiber, that we are learning here. So what are the various sources, and we'll compare that sources with respect to the single mode propagation or multi-mode propagation. Similarly, that sources we compare with respect to the step index fiber or a gradient index fiber. Now, given source, it emits a light. When it emits a light, it has some radiation intensity, and that radiation intensity gives us the spectrum, or it gives us the radiation pattern of the given particular source. So now we consider here a light emitting diode or a laser diode. What will be the emission pattern, or we can say that from the given particular source, how your light is emitting from the this particular device. That pattern we are learning here. So you know that a single tube or a bulb, it emits the light in all the direction. But in the case of optical fiber, whichever the source we have, that will emit a light in a forward direction. So that your light will be propagating through the fiber, and that some of the light, okay, so we say that when we have the source, if it has the emission pattern is likewise, and if the fiber core is small, so then this particular light will not emitting through the fiber. So in that particular core, that is nothing but the loss. This one, if we have a source here, it emits the light, but we have the core of a fiber is small, then this is nothing but a loss. In that case, we need to come bring that fiber near to the source here. So whichever the coupling mechanism we are using to connect the source, so that all the light emitting from the source, that will be propagating through the fiber itself. So we need a proper coupler here. Or we need to choose a source in such a way that that emission pattern will matches to the core size of a given particular fiber. Or we can say that a numerical aperture of a given particular fiber, so that all the rays are accepted by the fiber, and then it will propagating through the fiber. So based on that, we should know that what are the major requirements for the source. While learning, we should know that what are the major requirements of a source, so that your optical fiber communication can be tasteless. Here we say that whichever the information that is in the form of electrical energy, that will convert it into a current, and that current is there that will convert here in the form of a light or optical light, because your source is converting that electrical, that is current pulses, to the optical light, and then that light is propagating through the fiber. So here what coupling mechanism we are using, so that all the light emitting from the fiber that will launch inside the particular fiber. So here the power launching inside the fiber, that is the important parameter while we are learning the source here. Similarly, what here at the end, whichever the power coming from this particular fiber, all the light is to fall to the detector. That's why the detector is to be near to this core of a fiber, so that again here we require a coupling or a coupler here, so that all the light coming out from this particular fiber, that will fall on the detector there. So we need to learn that what type of coupling is necessary here at the uh, receiver side or at the fiber end, so that we'll get that all the output, so that efficiency of the fiber or a efficiency of fiber communication depending upon that source and fiber coupling, and a fiber and a detector coupling. So total link, if you consider that, a total link consists of your coupling at the source and coupling at the detector there. And then another parameter that is about the power launch inside the particular fiber. So what are the various optical sources and what are its emission pattern? So that we are learning. Just we say that light emitting diode and laser is there. Now what are their emission pattern and how that light is emitted from this particular sources that we are learning here. So generally we say that a light emitting from the LED, that is a incoherent, and if you see the laser, that is a coherent one. So that's why we can say that LED is about incoherent source and laser is about a coherent source. Because of that coherent source nature, so then single mode fiber can be used for the laser here. Because of that incoherent source, so we can that for the given particular source, multi-mode fiber is suitable. So now we'll go one by one. What are the various requirements for the given particular fiber so that optical fiber communication can be take place there? One, a size and the configuration, that size and configuration that will be compatible with the launching light into an optical fiber. So for a given particular source, we say that that source emit the light, that is whichever the light emitting from the source, so that all the light from the source that will be coupled into the fiber. So that's why the size and the configurations regarding what is the radiation pattern of this particular source and what will be the core size of this particular fiber. So means we say that here the acceptance angle, or you can say that a numerical aperture of a given particular fiber. So in general we say that light is propagating through the fiber, that is depending upon that acceptance angle. So that's why the source emit the light, that radiation pattern or emission pattern of this particular source that belongs to the acceptance angle of the fiber, so that all the power, all the rays emit from the source that will be coupled inside the fiber. Means power launching, or we can say that light launching from the source to the fiber is takes place here. So in general we say that a source we have a radiation pattern that will be unidirectional. But if you see that a radiation pattern, this is about a bidirectional. So in the case of this first lobe, another lobe here, so only if we keep the fiber here, only this particular radiation emission from the source that will be coupled to the fiber. So this is not this source, okay, it will not couple. So in general we say that a light emits, likewise this one is about a light emit from the source in this direction. If it is a unidirectional, so then it will couple. If it is a bidirectional, then what happen? Only this portion will be coupled to the fiber, and this one is nothing but the loss for the given particular fiber. So in ideal case or ideal condition, we need to consider that emission of a light only in unidirectional, so that we can calculate the efficiency or a output power coupled to the particular fiber. Okay, so we can calculate that. So now we say that whatever the electrical signal is there, and that will convert in the form of a light. So that's why the next parameter that is about a requirement is about, so whichever the conversion of that electrical signal that will accurately convert, you can say that electrical signal whichever that we have, that will convert into form of a elect that is about a light. So means for a given particular source, it must accurately track the electrical signal to minimize the distortion and noise. Okay, so that is about accuracy regarding what, a distortion, or we can say that whatever the noise is present, okay, we have from this particular signal there. So now this is about electrical signal. So that requirement is about what, it must accurately track the electrical input signal. Okay, that is about the requirement, so that there won't be any distortion or a noise. So that's why we say that your source that will produce a light from the electrical input, so that's why it has some particular linear output. Source must be a linear there. Then the source, we say that light emitting diode or laser diode, the mechanism of generating the photon of a light or emission, it is depending upon that whichever the material we have. This one is about valence band, and then it has a conduction band. So in the valence band, it has the electrons. Sorry, in a conduction band it has electrons. In a valence band it has a holes there. Now in between that, this one is a gap, and that gap has some energy. So we can say that energy gap here. It has some energy. So that's why we say that it's about a energy gap. And then at some applying some particular bias or at some particular temperature, electrons are exciting from the higher energy band to the lower energy band. And then a recombination takes place. And due to that recombination, it emits that a photon of energy. And that photon of energy is depending upon that what will be the energy gap voltage. Now we should know that how many number of electrons and photons, okay, means we should know that electrons and holes are combined so that it emits, because when electrons are moving from the conduction band to this valence band, so they lose their energy, and that they lose the energy in the form of a photon of energy, or they lose the energy in the form of a heat. So now we consider here, so that whatever the photon of energy generated by this electron, it produces some particular photon of energy, and that photon of energy is depending upon the what will be the electrons and hole combination. And then that photon of energy will give us the what will be the wavelength of the given particular source. So means we say that a lambda is equal to what, that is about hc by whatever the photon of energy, that is about E. So h is a Planck constant and c is 3 into 10 power 8, that is about light velocity of a light here in free space. And E is nothing but what? A energy. That is about a photon of energy. E is a photon of energy. And then that photon of energy gives us the what will be the value of the wavelength. So now that whatever the wavelength is generated means we can have a light source, it emits the light, and that light has some particular wavelength, and that wavelength is depending upon that photon of energy. Now in the optical fiber communication, the light emits from the source, that LED or laser, so that it has some particular wavelength, it emits from the source, so that light should propagate through the fiber, and that light has a low losses and a low dispersion. As we have seen earlier, that losses are depending upon that length of the fiber, that losses are dependent upon what will be the operating wavelength of the fiber, because we say that a ray light scattering that will be occur at a shorter wavelength, or intrinsic absorption or extrinsic absorption is depending again upon the wavelength. So all the losses we relate to the what will be the operating wavelength. So now that what we can say here, whichever the source we are selecting, that source should emit a light at a wavelength where the fiber has a low losses and a low dispersion. That is about from the source side. And similarly at the detector, the detector is able to detect that particular wavelength signal. So means whichever the source we are using, and that source has some particular operating wavelength, that operating wavelength supported by the fiber, as well as the detector detect that particular wavelength. So then we can say that another requirement is about that wavelength, operating wavelength of a source of a detector there, so that there will be a low losses, low losses, or we can say that low losses at a low dispersion inside the fiber. So now losses means what? Losses inside the particular fiber at a particular wavelength, and a dispersion means what? A pulse broadening. Pulse broadening means what? That pulse propagating through the fiber, and we are receiving the pulse here, that broaden here. That is about a pulse broaden. So the requirement for the source here, the source should emit a light at a given particular wavelength, so that they have the low losses and a low dispersion. And we have a detector. That detector will detect those particular wavelength signal efficient. So efficiency of a detector here, that will be based on the wavelength here. That will be the requirement. Then another requirement is about, for a given particular source, that source is capable for generating a signal or a light, and that light will work at the larger operating bandwidth, or we can say that wide bandwidth, whichever the source we are using, that has the wide bandwidth of a operation. Now wide bandwidth of operation means what? If for a given particular source we say that it will work at a wavelength, and then that spectrum we say for a given particular source, or you can say that a mode field diameter of a source, that will give you the what will be the bandwidth here. So that whichever the input we are providing to the source, that is about electrical signal, or you can say current pulses, that will be converted by the source over a wide range of a bandwidth there. So now that input can be of a audio frequency, or we can have the highest frequency there, so that that particular input that will be converted by the source. So that's why we say that it's a source that will work or that will operate at the wide bandwidth. Then next is about a coupling efficiency. That coupling efficiency at the source as well as the detector. Now what will be the coupling efficiency at the source and detector? Means whatever the power output power from this fiber from the source, that will couple to the source here. So that will be the coupling efficiency. So now it is depending upon that emission pattern of a source. Now we say that light emit from the source, that must couple sufficient optical power to the fiber, so that we can minimize the connector loss or coupling loss at the from the source to the fiber here, because we say that we require a coupler or a connector there at this particular place. If we make it that source and a fiber nearer using the connector or a coupler, so that maximum power will be coupled from the source to the fiber there. If that coupler is not capable to connect the source and a fiber, in that case there will be attenuation occur at the particular place. If that distance is large, so power loss will be takes place, as well as there will be losses through the due to the connector. So we should consider that a source is to couple the maximum optical power to the fiber, and that loss is to be minimized. That is at the source. Similarly at the detector, similarly at the detector, whichever the light coming from the fiber, that will be detected by the detector. So means all the light coming out from the fiber, that will be detected by the detector. So here the coupling efficiency at the source and a coupling efficiency at the detector. Now here it will be a connector, or we can say that a coupler. So now if we keep detector nearer to the source, sorry, nearer to the fiber core, so that all the power can be coupled from the fiber core to the detector. So that's why a coupling efficiency of a source and a detector is important, so that at the source that losses due to the coupling, or at the detector the losses due to the coupling is to be minimized. So means source must couple sufficient optical power to the fiber, and detector at the detector fiber must couple all the power to the must radiate all the power, and this detector must detect all the light source, okay, light from the fiber there, incoming rays from this row, that fiber core, that will be detected by the detector. So that's why we should know that what will be the coupling efficiency requirement for the coupling efficiency at the source as well as the detector, so that your detector will detect maximum signal and will get that maximum output at the detector there. Next is about, we say that a source will work at a wide bandwidth for a given particular signal, but again a source should have a very narrow spectral width, or we can say that instead of a spectral width, say that a spectral bandwidth. Okay, so don't get confused. Spectral width or spectral bandwidth, or in another way we can say that a line width. So why we require a narrow spectral width or a spectral bandwidth, or you can say line width here? Because we can minimize the dispersion. Now the phenomena of a dispersion means what? We have the a source. When source couple the light inside the particular fiber, means this is about a pulse, and we are detecting the pulse. That pulse will broaden. Simply we say that the dispersion is what? We have a pulse, current pulse there. When it will propagating through the fiber, then pulse broadening takes place. Now this is about a pulse width. But in the case of here, that pulse width will be increases as well as the amplitude decreases. Now this width here, if you see that from the input side and from at the output side, that pulse broadening takes place, that is called as a dispersion. And that pulse broadening is depending upon that spectral width. Because we say that for a given particular source, now this is about a source now, and this one is about a emission pattern of a source here. But source has particular spectral width, that is about, we can say, we will get that mode field diameter or a mode field diagram of a source. So according to that we can find out what will be the mode field diameter, and that what will be the spectral width there. Now in the case of a source that have the a spectral width, we are expecting it is to be a narrow one. So if that spectral width is a narrow, then the spectral component for the given particular range will be small. So generally source emit the light, and that has a various spectral components, and that has a frequency of f1 to fn. Now from the frequency f1 to fn, so each frequency component when it is propagating through the fiber, the last frequency component first came to at the detector, and first became later. So that's why the dispersion occurs. So at the detector, we are able to see that first frequency component, then another frequency component fn minus 1, then fn minus 2, fn minus 1, 2. Okay, likewise this one, and then at the end we are getting that f1 here. So that's why the spectral width will tell you what will be the dispersion. If that spectral width will be narrow, okay, narrow spectral width, then that F1 to Fn components will be a small, okay, and because of that F1 to Fn component small, the dispersion will be a small here. Means to minimize the dispersion, okay, to minimize the dispersion, narrow spectral bandwidth or spectral width is required to minimize the dispersion. So whichever the source we select, that source has a narrow spectral bandwidth, and that narrow spectral bandwidth that will be used to minimize the dispersion. Now then another role is there for the given particular source. That source is to be work for the multi-mode or a single mode. As we have seen in the dispersion, if we have a single mode fiber, no dispersion. If we have a multi-mode fiber, because we can say that dispersion is about a intermodal and intramodal. So intermodal dispersion is not there in a single mode fiber, but intermodal dispersion will be there in a multimodal fiber. Now, similarly, that dispersion can be minimized if we are using the graded direct fiber. That dispersion is related to the type of a fiber, but again, if we choose a source in such a way that which has the narrow spectral bandwidth, then whichever the fiber we are using, will get that low dispersion. So means either we can there are the scope to select the fiber as well as the select the source here to minimize the dispersion there. Then another is about what that source is to provide a stable output. Stable output means what? At any given condition or any ambient condition changes or any environmental condition changes, that source must capable of maintaining a stable optical output. So means if in this particular case of is here LED or laser, if supposed to be any environmental condition or ambient temperature variation is occur or ambient condition changes, so in that case source should not decrease their optical output power. Source should provide a constant optical power at the given particular ambient condition. So we consider that whichever the source we are using, whether it is LED or a laser, that source must be capable of maintaining a stable optical power or stable optical output, and that will be not affected by, okay, that will not be affected by any ambient condition or any changes in the temperature or any changes in the environmental condition. If any changes occur, that source is to be provide a stable optical output throughout the communication there. So that's why the requirement for the source that will provide the stable optical output power. Next, we consider that source is providing the optical power that is a stable as well as a reliable one. Means it will generate that whichever the signal we are providing, It will convert that electrical signal into optical power, and then similarly at the detector, that will detect even if that light is small. Okay, level of that particular light optical power is small, even if that particular detector is going to be detected. So means from the source side, that source is able to provide the optical power, and that optical power, it will be highly reliable one, so that we can transmit the signal. Again, whichever the source we are using, that source is to be cheap, and that source is to be highly reliable. We are using a source that is LED or laser, that will be highly reliable one, as well as they are, as compared to the price, they should be a cheap one. So now these are the major requirements for the optical source, and with this we can consider that particular requirement while selecting the optical source. But in general, if you see that whichever the optical sources we have, they are operating at a 1.1 and 1.6 micrometer wavelength, and at that particular wavelength, they have this is about a wavelength we say of the optical sources, and at that optical wavelength, that material loss and dispersion losses, that will be reduced at this particular operating wavelength. So that's why we choose optical sources that will be operating at a wavelength between 1.1 and a 1.6. If we choose the sources that will work in between this particular operating wavelength, so that's why we can minimize the material loss and a dispersion here. And in this particular wavelength region, so we can use a gradient index fiber, and that gradient index fiber, if you consider that a dispersion can be minimized when that gradient index fiber is to be used as a multimode fiber, okay, multimode application. And in that case, if we use a source as a LED and a gradient index fiber, so that we can minimize the dispersion as well as the material loss. And so that's why with a source LED and a gradient index fiber, we can use this combination for a long distance communication, so that we can use a repeater after very long distance. Even if without repeater, with this combination, we can communicate for the, or we can transmit the signal for the long distance communication. So now that a combination of this, that will be useful for the longer distance communication there, because we use a gradient neck fiber, and that gradient neck fiber will reduce the dispersion there, and optical source in between this particular wavelength. So then the dispersion and a material loss will be reduced there. So for a given particular source, so what will be the losses and a dispersion? Similarly, if we use a laser, and that laser with a single mode of operation, so in that case, the dispersion will be low. But if we consider that a source of a LED or a laser, if you compare that, so generally a LED is full for the multimode fiber, then we can use that LED for the wider bandwidth, then we can use that LED for the longer haul application. But if you consider that a laser again can be used for the very long haul application there, and they have the extra wide bandwidth. So most of the application you can see that for the multimode of applications, so LED is used because of the it will operate with a multimode fiber.